Okay, so we'll continue talking about the chiral Lagrangian. The one thing I'll do from the start is, instead of talking about SU2 cross SU2, I'll do the SU3 cross SU3. So we have a field sigma, which goes to L sigma R dagger. Sigma is a function of X, and L and R are not. They're constant unitary matrices. They're independent. Sigma is parameterized as e to the 2I pi matrix over F. We discovered F could be identified with F pi, where F pi is 93 MeV in my normalization. And the pi matrix for SU3 looks like what Gino showed you the other day with a slightly different normalization. The pi plus and the k plus up top, k0, pi minus, k minus, k0 bar. And the quantum numbers of with what hypercharge and isospin, pi plus, pi 0, pi minus, this is 1, and then hypercharge 1 up here. We have the isospin a half, we have the k plus, is 0 over here, a minus a 0 bar. And then we have the eta in the center there. And the way to understand, again, why these particles with these quantum numbers are mapped onto a matrix like this is to remember that under the SU3 vector transformation, or SU3, I guess that's written, Gino's been writing as L plus R. That's the same as Gilman's SU3. The variation of pi matrix is the commutator of the generator with pi. And so if you take T3, which is 1/2, 1, 1, 0, 1 minus 1, 0, or you take T8, which is 1 over root 12, 1, 1 minus 2, which is proportional to y, which is a third, 1, 1 minus 2. Then when you commute that, for example, you see that the k plus, when you commute with T3, you get a 1/2 when you multiply on this side by T3, and you get a 0 when multiplying on that side. And so the k plus has to be one of these I3 equals half states. And then when I commute it with y, I get a 1/3 when I act on this side, and I get a plus 2/3 when I take the other part of the commutator from that side. So it has to have hypercharge 1. And so I identify this part of the matrix as being the k plus. And you can do the same thing for all the off-diagonal ones. It's very straightforward. For the diagonal ones, notice that if I just look at where the etas are, they're proportional to the T8 matrix. The T8 matrix commutes with not just T3, but all of the isospin generators, like T1, which is 0, 1, 1, 0, 0, so on, T2. So they all commute with a matrix like that. Therefore, it must be an isospin singlet. There's only one isospin singlet on this picture here. It's the eta. So you can map out very carefully exactly why these particles are mapped onto that matrix. And the normalization of the matrix is such that trace pi squared looks like a mass term, 1/2 pi 0 squared plus 1/2 eta squared plus pi minus plus k plus K minus plus K0, K0 bar. This is a Hermitian matrix, so K minus is the dagger of K plus. And K0 bar is the dagger of K0. So then we saw that you can write down kinetic term. F pi squared over 4, trace d mu sigma dagger. That is the most general theory up to 2 derivatives, except we now want to include the mass term, the quark masses, and understand what exactly is making these things not exact Goldstone bosons. Because it's like in the case of a spontaneously broken U1 symmetry, you've got this wine bottle potential. If it's got an exactly flat set of vacua, then you have an exactly massless Goldstone boson. If you tip it, now the degrees of freedom, there's one unique vacuum, and the oscillations around that vacuum correspond to a harmonic oscillator for small oscillations, and so you get a massive particle. So that's what the quark masses do. They explicitly break the SU3 cross SU3 symmetry of massless QCD down to the vector subgroup. So we have a combination of explicit breaking to a smaller subgroup, and we have spontaneous breaking at the same time. And so we are treating the mass matrix as a small perturbation, and of course, that's only justified if it actually works. So we'll have to see how well it works. So the mass matrix can be taken, as I said, as the QCD would have been invariant if we had taken the mass matrix to transform like this may be the opposite of what I said yesterday, RM L dagger, in which case M dagger goes to LM R dagger. Dagger there. Now, the fact that we're actually using a real mass matrix in the end doesn't matter. I want to keep track these 2 different pieces individually. So this means that what I put into QCD is Q bar right M Q left plus Q bar left M dagger Q right. This might have been the opposite in my lecture yesterday when I put the dagger. So if M transformed like this would have been invariant. And so the low energy theory should have the same property. However, while the Lagrangian is linear in M, there's no reason for the chiral Lagrangian to be linear in M. That's a dynamical statement. We don't know anything about the dynamics. So but in the spirit of effective field theory, we're going to be doing a Q over lambda expansion. And then the question is, what is Q? Well, Q is a momentum of the meson, or it'll be the mass of the meson. And lambda, well, the only scale we have in the problem is F pi. What actually happens is you find that it works better than that. If it only was a derivative in powers of momentum over 93 MeV, that wouldn't be very good. It actually goes farther, and there are theoretical arguments for why you might want to assume that this lambda is going to be roughly 4 pi F pi, and that comes from a scaling, some arguments called naive dimensional analysis. And what you're saying is basically is that you sort of expect that your coefficients of your operators in your effective theory should be roughly equal to the quantum corrections that they receive. It would be unnatural for them to be smaller because quantum corrections would then make them big. They could be bigger, but there's no reason to assume that. So, but what we do is we sort of assume that lambda is on this scale, which is about a GeV. Okay, but still, all operators have to have unknown coefficients that we're going to fit to data. And so we'll make this assumption, but in the end, we're going to be fitting to data. So we'll see if there's a problem with our power counting. And one famous exception to where the power counting fails completely is the delta I equals a half rule, where decays are much, much bigger than you would have expected in delta I equals half compared to delta I equals 3/2. So you just, but this is sort of a rough guess. So what we're going to find is that, right, well, let me continue with this here. So the question is that how do we include such an M in the chiral Lagrangian? And we can do it by writing Lm, and I'm going to write it like this way, lambda, how do I want to do it? Lambda squared F squared times some number that we don't know times trace M over lambda sigma. See, sigma goes like L sigma L dagger. So this picks up an R dagger, an R M L dagger, and then sigma picks up an L R dagger. And so these cancel, and then this one cancels with that. So this is invariant. And you have to do plus Hermitian conjugate. And for convenience, I'll put a 2 here. And then because this lambda cancels that lambda, so the reason I did this is dimension 4. That's the dimension the Lagrangian has to have. And then everything else has to be dimensionless. So I have an M over lambda. So I made a mistake here. This is M quark, not M pi. So let's see then what the prediction is, okay? Because we've got some unknowns here. What is M? M is the mass matrix MU, MD, MS. We're working on a mass eigenstate basis for the quarks. We have, okay, and so if we, and as I said, we have M up on the order of 2.5 MeV, M down is about 5 MeV, and M strange is about 100 MeV. But you don't actually need to know these numbers. I mean, it helps, of course, if you want to predict things, but these numbers are not something you can predict from the chiral Lagrangian, okay? But we'll see that in the mid-70s, Weinberg surprised everybody by showing that the chiral Lagrangian can predict what the ratios of the quark masses are. That's a calculation I'll do. So now you take this operator and you expand it to second order in the pion field to find what the masses are. Okay, and what you find then is that the Lagrangian is equal to a constant piece, which is some vacuum energy contribution, plus at order pi squared, you get, minus m pi squared pi plus pi minus mk, let me call it m pi plus squared, minus mk plus squared times k plus k minus mk0 squared, k0 bar k0, minus 1/2 times, and now I'm going to make a 2x2 mass matrix for the I0 and the eta. And there'll be a 2x2 matrix I'll call M0 squared, sandwiched between these two neutral mesons. And when you expand that, what you find is that m pi plus squared is equal to, I'm going to define C lambda is defined to be lambda twiddle, just an unknown parameter. There's an overall unknown parameter times, now these F's are going to disappear because sigma, every time you have a pi, comes with a 1 over F. So if you expand to order pi squared, the F's cancel. this lambda cancels one of the lambdas. C times the other lambda is lambda twiddle. So everything's proportional to lambda twiddle times quark masses. So you find that this is mu plus md. M A plus squared is equal to lambda twiddle times mu plus ms. And mk0 squared is equal to lambda twiddle md plus ms. And then this 2 by 2 matrix here, m0 squared, is equal to lambda twiddle times mu plus md, mu minus md, mu minus md, and then 1/3 mu plus md plus 4 ms. This just comes from taking your sigma field, which is an exponential in the pions, expanding it to order pi squared, taking the trace of this matrix times the 2 pi matrices. Can anyone tell me why the off-diagonal term here is a function of mu minus md? Or why does it vanish when mu equals md? Isospin, exactly. You see, if so far, there are two main contributions of breaking of isospin: the difference between the up and down quark mass and the difference in the electric charges of the two quarks. We don't have electric charges here yet, so the quark mass difference is the only thing that breaks isospin. If you look at this diagram of the particles, the pi zero is part of an isotriplet, eta is an isosinglet. They can't mix unless you have isospin breaking. And that's why this mixing term is proportional to mu minus md. Now, if we ignore isospin breaking, then you set that to 0. We basically have mu equals md equals m bar. We're assuming they have roughly the same mass. Then what you find is that there's a relationship here. We've got, in isospin breaking, there are the independent masses are m pi squared. The pi zero is degenerate with the pi plus and pi minus if you have isospin symmetry. You've got your mk plus, your mk squared, which is the same, mk plus squared and mk zero squared. And then m eta squared. Okay, they correspond to these 4 different isospin multiplets that you see here. This one, the pion and the eta, that's 2, and then 4. So you have 4 different masses that you have formulas for, but we can't deal with them directly because they've got all these unknown parameters in them. And you, sorry, what?
3 masses, K plus and K
I'm sorry?
K plus and K naught are isospin.
They are not degenerate.
I mean, mu equal to md, they have the same mass.
Oh, sorry. Yes. Yes, I'm sorry. These are degenerate in the isospin limit, mk squared. We have 3. Okay, now in this limit, how many parameters do you have? Well, you've got m bar times lambda tilde and ms times lambda tilde, ms times lambda tilde. So you've got 2 parameters, unknown parameters, 3 masses, okay? And so there's a prediction, and this is the Gelmano-Kubo prediction, which can be written as 3 m eta squared plus m pi squared is equal to 4 mk squared. Okay, and these, if you look up the particle data book, you have to do an isospin averaging over the isospin multiplets. These agree to better than 1%. was a tremendous success, early success of SU3's symmetry. With the assumption that the masses come from, see, at the time when Gelman did it, QCD wasn't a theory yet. So what the main assumption was is that there was a symmetry breaking parameter which transforms like this. Okay, so with that assumption, Gelman was able to come up with, and that linear perturbation theory in the breaking would work. With that, he came up with this prediction. Another source of symmetry breaking is the electric charge. Explicit symmetry breaking. We have in the quark theory, we have the electric charge couples to the current E times Q bar gamma mu E left capital Q little q. So only just put lefts on the quarks. There's a projector here, and I'll call this Q left plus E times Q bar left, Q bar right, gamma mu, capital Q right. Q right. This is a generic way that a gauge boson would couple to the quarks through some coupling to the right-handed quarks and to some possibly independent coupling to the left-handed quarks. So you can use this general formula you can generalize this formula easily to include W's. For W's, this would be the weak coupling, and these Q's would be the W generators. For electromagnetism, we have a vector-like symmetry, which means these are the same, actually, which is charge 2/3 for the up quark, minus 1/3 for the down quark, minus 1/3 for the strange quark. And by a fluke, this happens to be traceless, so it actually is contained in SU3. This is a linear combination of isospin and hypercharge. So how did these things transform? Well, the reason why I broke this up into Q left and Q right, so remember, we're going to do the same game we did with the quark mass matrix. We're going to say, this breaks the symmetry, but if Q left and Q right transformed under the symmetry, I could make the theory invariant. So I would have to have Q left goes to L, Q left, L dagger. Because both quarks here are lefty quarks, unlike in the mass matrix case. And I'd have to have Q right goes to R, Q right, R dagger. So one way to put photons in, obviously, is to take your ordinary derivatives and turn them to covariant derivatives, where what we have to do is that the covariant derivative on sigma looks like d mu plus I E A mu times Q left sigma, because Q left can only act on the left side, it can't act on the right side. And then we have to have a minus I E sigma, sorry, A mu. I guess, yeah, times sigma Q right. That's because sigma, remember, goes to L sigma. So under a transformation of L, it gets a generator on this side with the I theta, e to the I theta TA. But under the right, it goes like sigma R dagger. And this dagger is why there's a minus sign there. If you put a plus sign, you'd immediately see a problem. Because electromagnetism is a vector-like symmetry, right? We've already seen that under SU3 vector, the pions transform like the commutator of the generator. So if we had put a plus sign here, we would have found that the electric charge is proportional to the anti-commutator of the generator, which wouldn't make sense. You would get crazy charges for your pions. Okay, so this minus sign is critical. And this just gives you the usual types of diagrams where if you have a pion here, you can have either a direct coupling like this, or you can have a Siegel type term coming from the fact that you're looking at trace d mu sigma dagger. And so in the Siegel term, you're taking the A field from both of these, while here you're taking a derivative from one and the A from the other. It's the usual thing for a scalar field. But we're not done yet. After all, Q is just some symmetry breaking parameter. It doesn't have to go along with the photon in the low energy theory. So we can make operators that involve Qs that don't have any photons. And in fact, we have to, because in principle, if you have a diagram like this or a diagram like that, where that's a pion line and these are photons, they're going to need renormalization. There has to be a counter term that knows about 2 powers of insertions of the Q matrix that don't have any external photons. So this will correspond to the electromagnetic contribution to the meson masses and other interactions. So we have to ask ourselves, how can I build an invariant operator out of these Qs and sigmas? Each Q is going to go along with a charge E. So if I want something that starts, the lowest power I can do is going to be order alpha. So the question is, what operator can I build out of 2 Qs and sigmas and no derivatives? You can't build one with 1 Q. If I put a Q left here, I put a sigma here, but that's not going to be invariant because this has an R dagger here, but this transforms with an L. So I could put another sigma dagger, that would work, but now this is trivial because this is 1. So you see, you can't make one with a single Q, but you can make one of this form. Like that. Now you see why I insisted on breaking the charge up into a left and right pieces, even though they're the same matrix, okay? But in terms of symmetry properties, I have to think of them as independent, and there's one of each here. One observation you can make right away is that if I had gauged an axial type gauge symmetry, where left and right matrices had opposite sign, then the contribution to the meson mass would be opposite sign. And I actually used that in my PhD thesis, where I was making a theory of composite Higgs bosons. A Higgs boson has to transform like SU2 cross U1. And so I thought, oh, look, the K-on transforms like like a doublet, exactly like the Higgs under strong hypercharge and strong isospin. So it looks like a great example of a composite Higgs boson, except it's got a positive mass squared. But to make a real Higgs, you have to put in a negative mass squared. So if you say, oh, well, maybe I could put in a new type of gauge force where left and right had opposite signs, and then this will contribute a negative mass squared, and then you could get a Higgs effect. And that was using these Lagrangian, only not for the strong interactions. I was lifting it up and saying there's a new type of strong interactions high up that creates a Goldstone boson like the K-on, but it gets a negative mass squared and breaks the weak interaction. So let's use this to compute the mass difference between the pi 0 and the pi plus. So we can write down L alpha, and write this as some unknown parameter. And this time I'll write an F pi fourth times an alpha over 4 pi. Since I have an unknown parameter, it doesn't make any difference what I put it in front really, but the alpha has to be there for sure. And then I'll write trace Q left, sigma, Q right, sigma dagger. And I expand to second order in the pions. And what I find is that this is C F fourth E squared times 2 over F squared times trace of Q left times the commutator of the pi matrix commuted with the commutator of the pi matrix commuted with Q right. And this is equal to minus 2 C E squared my notes were wrong. This should have been a lambda F squared. Lambda squared F squared. And then I used the fact that lambda is about equal to 4 pi F pi and turned it into a just F, got rid of the 4 pi squared from here and turned it into E squared F fourth. So there's an E squared here with no pi's. And there's an F squared, which gives you the dimensions for mass squared. And then there was a pi plus, pi minus, plus K minus. So it tells you that this operator just gives mass to the charged mesons, which is what you'd expect. And it's the same for the K plus and K minus, because as far as the charge is concerned, they're equivalent. It doesn't see, there's no quark mass in here. Can't tell that there's any difference between the two of them. Now you might ask, is this the mass, or do I have to also compute loops? So I should also have these loops here. This is a pi plus or a K plus. Where this is this operator here. Well, as usual, the coefficient here is going to be scheme dependent. I have to know how I deal with the infinities here to know what value that has to have. I am doing an expansion here where I'm looking for the E squared contribution, not the E squared M quark contribution. So I can take the quark masses to be 0 here for the mesons, and so I can treat the mesons as massless. And then if I use dimensional regularization, these diagrams cannot contribute to the mass squared of the meson, because dimensional regularization's beauty is that it never introduces mass scales upstairs the way a momentum cutoff does. So all the mass scales are downstairs. They come from the couplings here. They involve 1 over F's. And dimensional regularization can never give you a mass upstairs that's not included in your integrand. So if I have a massive meson, yes, it can give a mass contribution. But for massless mesons with massless photons, it can't. And so these diagrams will not contribute in MS in a minimal subtraction type scheme. And this is the whole story. So that's the scheme that is useful, and it's very useful to use dimensional regularization because of this property that you don't introduce new powers upstairs. So you know that, for example, one of the beauties is that I don't have to worry that there's some operator with 18 derivatives here that when I put it in a loop will renormalize something low because it's got 18 powers of F downstairs, and dimreg cannot ever put powers of F upstairs. So I will never get an operator like this that has, or, you know, I'll never be able to take something which has 18 powers of F downstairs and end up with an answer that has an F squared upstairs. Is there a question? Yeah. So that's a higher order correction. It'll, you can compute those, yes.
But then we cannot make it.
No, then you have to include the, then dimreg will give you a contribution from this graph to the thing that goes like E squared M quark. So when you include this now, you get that m pi plus squared is equal to lambda tilde times mu plus md plus alpha over 4 pi delta squared. I'm just writing it like this. It's some unknown shift. But the only what I have learned is it's the same unknown shift for the k plus and k and pi plus, and no shift for pi 0 or pi minus. And so Weinberg noted in the mid-70s that you could take the following combination of meson masses. And the electromagnetic contribution from is the same on both of these, and it cancels. This unknown parameter, this parameter delta drops out. And this is equal to mu minus md over mu plus md. We're including isospin violation now. And I'm not assuming mu minus md is small. And the combination 3 m eta squared minus m pi 0 squared over m pi 0 squared was equal to 4 ms over mu plus md. And so what you see is that the unknown parameters delta and lambda tilde have dropped out, and that the result, because it's dimensionless, is a function of just quark mass ratios. So from this, by putting in the measured masses, you can compute the two independent mass ratios. Mu over md is equal to 1/2, and md over ms is about a 20th. I mean, this is approximate. It's pretty close. And this is sort of startling that you could get this information from the mesons. It also is sort of interesting because isospin is a very good symmetry. Isospin requires mu to equal md, but here we find mu is 1/2 md. Well, the reason why isospin is good symmetry is not because we're taking the violation of isospin is measured by mu over md, but it's the difference of mu minus md compared to other mass scales. Okay, so for example, mu plus md or these things, but actually what comes into the calculation in the end is mu minus md over lambda. So typically what we find is that isospin breaking is at the percent level or something. So what I want to do now for the rest of the lecture is to tell you how to include baryons. So the baryons are an octet also. So the baryon, I'm talking about the octet baryons. So again, Y isospin. It's a very similar picture to the octet of mesons. Where here you've got the proton, the neutron, sigma plus, the sigma minus, sigma 0, sigma minus, and lambda, and cascade 0 and cascade minus. And so the baryon matrix looks very similar. It's sigma 0 takes the place of the pion. the lambda takes the place of the eta. And then the sigma plus and sigma minus take the place of the charged pions. The C plus and C zero take the place of the charge minus take the place of the charge cans, and the neutral C. What am I doing here? Proton, neutron, C minus, C zero. This is not a Hermitian matrix. Instead, what we have is B bar. This is a Dirac fermion matrix. So B bar looks like the Hermitian conjugate of this, but with the bar put over everything. Sorry. But how does it transform? Well, it turns out there's no unique way to say how it transforms. These aren't quarks. They're made of left quarks, right quarks. So this isn't a problem. It's just extra freedom for us. We can specify how we want to make it transform, and I'll show you how you can, why it is up to us. Suppose I took that the right-handed baryon transforms like a right-handed octet. That seems like a pretty sensible arrangement. And B left transforms like a left-handed octet. Well, then you could come along and say, well, I'm going to define a new field. I'm going to define BR prime is defined to be sigma BR. And B left prime is defined to be B left times sigma. Well, now BR prime transforms like, well, this had an R dagger on this side, which cancels that R, but it picks up an L on this side. And this one transforms like L, DL prime, R dagger. And so I can put them together and have the whole Dirac field transforms like L, B, L dagger, or dagger. Now you say, well, actually, this looks like more convenient than that one because I don't have to specify different transformation properties for the different chiralities. So the point is the chirality of a baryon is not a sensible thing to be interested in because the baryons are heavy and masses break chirality. So the chirality of a baryon is not interesting. So that's why we were able to move it around by adding massless ions, which have chiral properties. So the interpolating field, your interpolating field could be a baryon of some sort, and mine could be a baryon of a different sort with lots of different massless pions. That also creates a baryon. So what is a good basis for the baryons? Oh, they're all equivalent, but one of them is particularly nice. Let's go back for a moment to this one here. We could write a mass term like M naught times trace E left bar That has an L and an L dagger. And then we put a sigma. That absorbs that L dagger and puts an R dagger here. And let's see, sorry, I have a 161. Typo in my notes, then I could put a sigma dagger here. I could write a mass term like that. Notice that I could write a mass term that doesn't have quark masses in it. The baryons are heavy, even if the quark masses are 0. Now you expand this, and you can find that this is M naught trace B bar left, B right, plus, and then you can find that there's a twice M naught over F trace B bar I gamma 5. I think there's a commutator of pi here with B, not sure. Now, the reason why I don't like this basis, notice that the pion coupling is not involved with derivative. Now that seems a little funny because a pion is supposed to be a Goldstone boson and it has a shift symmetry of sorts, okay? You'd think that pions have to be derivatively coupled. And the answer is, it is, but it's hidden because of the gamma 5 here. If you take a non-relativistic spinner and you put a gamma 5 in it, it's proportional to the momentum of the baryon. So this is actually proportional to the momentum. I mean, sorry, this is proportional, this matrix element with spinners with a gamma 5 would be proportional to the momentum transfer given by the pion. And so you'd actually find that this vanishes as the pion does not deliver any momentum. But it's hidden. So it's not a very nice basis. Still, this is the sort of basis that was traditional in the beginning where G pi NN is couples to nucleons with a gamma 5 and no derivative. Yeah.
The row is on EFT, but couldn't the variant.
I'm sorry, I couldn't hear that.
You're not the row is on the vector row.
Okay, so there are all sorts of other mesons I haven't included here, rho mesons and deltas and so on. The only reason I'm putting the baryons in here is because we use them as external states for our probes. So we have to include them. If we're not going to do scattering, if we're going to do scattering experiments where we create a row and scatter off something, we'd need that too, but we can't. Okay, it's too unstable. So in terms of the row would only affect things in terms of internal quantum fluctuations, but we're assuming that that's up at our UV scale. Our effective field theory doesn't have those. And we're also not going to include baryon-antibaryon pairs. We're going to use non-relativistic baryons here because PP bar production is above the range of our effective theory.
All the baryons are non-relativistic.
So all these are non-relativistic. I won't put in, the only antibaryons that can appear here is if they're coming from my beam. I'm using them as a probe. So instead, we're going to come up with a new basis for the baryons, which at first seems really weird, but it's really quite pretty. Let's consider an object C of x, which is e to the I pi of x over f. So C squared is equal to sigma. Now, sigma goes to L sigma prime, which is e to the 2I pi prime over f, which is equal to L sigma R dagger. How does C transform? Well, I can define it to be, well, it's equal to C prime, which is e to the I pi prime over f. It's the same pi prime. And I can define this to be L C U dagger of pi. It's some unitary matrix that depends on the pions. And the reason why I can do that is because I can just define U dagger to be just multiplied by C dagger, L dagger, C prime. So this contains no content, really. I've just defined U. There's some matrix U such that C satisfies this. Now, I could have also said that C goes to C prime, which is equal to V dagger C R dagger. Sorry, V C R dagger, where this is a function of pi. It's a very similar definition with a different matrix. But we know that C squared is equal to sigma, which goes to L C squared R dagger. And this has to equal C prime squared. And that I'll take for the first C prime, I'll take this definition. So that's L C U dagger. And for the second C prime, I'll use this definition, which is V C R dagger. But this has to equal that. Multiply both sides by L dagger on the left, R on the right. I get that C squared is equal to C U dagger V C. Multiply by C dagger on both sides, and I get that U dagger V equals 1, which means that V is equal to U. So what we've shown is that there is some U of pi, this horrible unitary matrix made out of pion fields, and I don't need to know what it is, but I can say that C goes to L C U dagger, which is equal to U C R dagger. Both transformations are equivalent for some U. Yeah.
Like either of the U's that you used yesterday.
I'm sorry?
So yesterday you had little U and big U. Oh, you had. Okay. So in the meson theory, now maybe it's a bit high.
Oh, sorry, my notation's clashing, huh? Well, sorry about the inconsistent notation. You obviously should have made Gino give all the lectures. Okay, so we have this transformation for some U. Now I'm going to say that I want my baryons transformed like B, U, B, U dagger under SU3 left plus SU3 right. Now, the first thing you have to check is the one thing we do know about the baryons is how they transform under the vector SU3, right? They're the octet. These are functions of pi. Notice that if I take L equals R equals W, which is in SU3 vector, left plus right, then you can easily check that U of pi actually equals W. Because we know how the pi's transform, because pi prime equals W pi W dagger. And so you can immediately see that with L equals W, U dagger has to be W dagger for this to be true. So these U's are a mess under transformations where L does not equal R, but where L and R are locked together in the Gell-Mann SU3, they're simple, they're just constant matrices. And then under SU3 vector, where these are constant, independent of pi, and that's good. That's the correct transformation law for a octet under SU3 vector. So I'm not doing any damage to the symmetry that is exactly realized after the symmetry break. So this is how I'm going to take the B's to transform, and now we have to figure out how to couple them to the pions. So an immediate thing is that it's now extremely easy to write down the mass term just write M naught trace B bar B. That's invariant because B dagger picks up a UU dagger, B picks up a UU dagger, the UU daggers all cancel. So even though U is a mess, we don't want to have to calculate, you don't have to, this is invariant. The kinetic term is going to be trickier because U's got dependence on the pions depend on space-time. We've seen space-time dependent transformations before, and we know that you have to turn derivatives into covariant derivatives. So what we have to do next is compute to define some currents made out of the pion fields. And so we define A mu, this is not the photon field, is defined to be I over 2 C dagger d mu C minus C d mu C dagger. It's a 4 vector. And under parity, the pi fields go to minus the pi fields. They're a pseudoscalar. So that means that C goes to C dagger, and they interchange with each other. And you find that A mu goes to minus A mu. And therefore, this is what we would call an axial vector. Now, if you also do the transformation on X vector, which you're supposed to do with the parity transformation, the spatial components will also flip sign a second time. So what you find is the time component flips sign, the space component does not, the way you expect for an axial vector. How does it transform? Well, you can check. You might be worried. There are all sorts of derivatives there acting on U's and U daggers, and it takes a bit of algebra to show that when I take C goes to U, C, U dagger, and these are X dependent, the derivatives of U's cancel out, and you find that A mu goes to U, A mu, U dagger. And so we call this the axial meson current. And if you expand it in powers of the pion, you'll see that it starts off at d mu pi. And this would have an f, and this would have an f squared, f cubed. So the obvious next thing to do is to compute the same thing with a plus sign. B mu is equal to 1/2. These are, I'm defining both to be Hermitian. C dagger d mu C plus C d mu C dagger. This is a vector current. Meson vector current. And it transforms when you do the algebra, which, as I said, is a bit messy. B mu goes to U, B mu, U dagger, plus U, D mu, U dagger. It looks like a gauge field. It's not. It's made out of scalars, pseudoscalars. The vector index is not coming because there's a vector field, but because I've got derivatives on pseudoscalars. But that means we can make a covariant derivative. We can define d mu is little d mu plus so you have to be careful. D mu b is defined to be the little derivative acting on b plus the commutator of b mu with b. Now, notice that both these, D is anti-Hermitian and a commutator is anti-Hermitian, so this makes sense without an I. This is the definition of a covariant derivative, and it transforms as U d mu B U dagger. So now we know how to write down an invariant kinetic term. Trace B bar I capital D slash minus M naught B is my Dirac kinetic term, and it's got meson interactions built in because it's got this V field in there. So the V field, if you expand this thing in pions, the linear term in d pi cancels because I have a d pi from this. If I take a one, this is one, this is I d pi. This is one, this is minus I d pi because the dagger. So there is no term that's odd in pions. V u looks like pi I d mu I plus order pi fourth with a derivative in it. And so this includes graphs that look like this. And because these are non-relativistic baryons, the gamma mu that you get here, if you pretend they're Dirac, the spatial gamma i's are small. They go like the momentum of the baryon, and the gamma zero term is big. So the leading term you get from this is these pions here with this pi d0 pi coupling, the gamma zero at the vertex. That's the leading non-relativistic term. And this is called the Weinberg-Tomozawa term. You may notice a pattern that Weinberg's name keeps coming up. Okay, so that's the end of my lecture. The last thing I'd want to do is say, well, how do I incorporate quark masses? I'll just say it really briefly, is that, remember our M goes like LM R dagger, or I guess I had it like RM L dagger. And that can't be easily directly attached to the baryons, which have the U's in them. So I can define CMC, that transforms like like UC R dagger. Let's see, how do I do it? Did I erase it? So I've got this, and I've got UC R dagger. So Right, so this goes like UC dagger, M goes like R, M, L dagger, and then I put a C here, which I take the other transformation law for the C, which is R, C, U dagger. And so this is equal to U, C, M, C, U dagger. And then the Hermitian conjugate also transforms the same way. And so I could start making terms that involve the mass splittings involving combinations of this. That's how SU3 violating mass splittings come about. And then the last big thing is how do you couple the A field to the baryons? So that's easy. You can write down a term that looks like trace B bar A mu B. That's invariant. But you can also write down another one, which is trace B bar B A mu. That's also invariant. There are two different ways you can couple A mu. So in fact, there are two independent operators, and what one usually does, one writes down L equals D bar D slash minus M by D slash minus MB plus, and then you have this A mu coming in two different ways. We have a minus F trace B bar. Okay, this is chiral invariant, but not Lorentz invariant. That's an actual vector, so we have to put a gamma mu, gamma 5, and then we put a commutator of A mu with B. And then we also have minus D times trace B bar gamma mu, gamma 5 times the anti-commutator of A mu with B. These being just two different linear combinations of those ways of connecting. And these D and F coefficients that can be matched to data by looking at semi-leptonic hyperon decays. So they involve the transition from one hyperon, from a hyperon to a nucleon and spitting off a meson. So on. So if you expand to, if you just put in the nucleons and you put in the pions, this will give you a d mu pi a n bar gamma mu gamma 5 sigma a over 2 type coupling. It's a derivative coupling of the pion to the nucleons instead of that gamma 5 coupling that we found on the earlier basis. And I like this one because it shows that the pion is only derivatively coupled, but it is equivalent to the other one with a gamma 5 coupling if you go to a different basis. But you have to be careful when you change bases, okay? So find your favorite basis and work in it. There was an astonishingly long debate in literature about whether the gamma 5 coupling and the derivative axial coupling were equivalent, and it's just because people didn't do the basis changes consistently. Okay, sorry to go over. Thank you.
Not working. The transformation properties for the sigma field, I could understand from its quark constituents like QQ bar. How to similarly understand how the baryon, its transformation properties as like free quark constituent. So you started with the assumptions like BR and BL both are adjoints under SU3R and SU3L. But if I think of them as three quarks, how can I connect it to their transformation property?
So if you think of baryons as a composite of three quarks,
yeah,
how do you connect that from that statement to the fact that you started with baryon being an adjoint of SU3L? Right there.
So you're talking about SU3 axial? What?
Like the BL going as LBL L dagger, right? I think that's what originally you wrote, right? BL goes as LBL L dagger, The second line.
I'm sorry.
Suppose I get through the one before. These lines.
So how would I couple the pions if I did it this way?
No. So thinking of baryons as
Oh.
three-quark composite operator.
So the baryons are a mess, right? Especially with light quark coming and going and antiparticles. We don't have any good feel for their chirality properties. Chirality is completely broken for the baryons. They're very heavy. So the chiral properties are sort of meaningless, okay? You can define it however you want under the axial transformations. And the thing is, because we can't really isolate a baryon and baryon plus a massless zero momentum pion, there's no way to distinguish between those states, really. They both create baryons. So you can add or take away massless pions at zero momentum. They have different chiral transformation properties, but they create a baryon just as well. They're just equally good interpolating fields for creating baryons. So you say a baryon's a three-quark state, but it could be three quarks plus a quark and an antiquark. That also creates a baryon.
Why do you assume that?
Assume what?
PL goes as LPLL tag.
So B is an octet. So if I erase the R's and just call this a vector symmetry, under SU3 Gelman, B goes to V, B, V dagger. So it's sort of natural to take the vector symmetry and say the left has its own vector-like symmetry, the right has its own. This might be a nice thing to do.
Can I make a comment? So I think what he showed there was just to show that at the end, these are ambiguous. While the only good thing we know for sure from nature is what is on the right, the transformation property under the vectorial group, because this is given by nature. So it's an octet. We know that the SU3 vectorial is unbroken. So an octet has to transform like V, B, what is written there. So that is, nobody can dispute. Okay, that is the only thing we know, right? Do you agree?
This is non-negotiable.
Exactly.
The constant matrix and lives in SU3 Gelman. How we lift its properties into the bigger group is up to us.
That's why these Xi are very useful, because then the Xi, this compensator, allow us to do whatever we want in terms of the nonlinear, or in terms of the G group.
And you just have to remember that a baryon field is any object that will create a baryon. And so I can add any number of massless pions to it, and it still creates a baryon, okay? But it changes its property under the full SU3 cross SU3. So then it just becomes my choice on how to create the interpolating field that has the nicest transformation properties.
So I was thinking like using this EFT, I cannot calculate proton, antiproton going to two pions.
No. You're talking about momentum transfer. The pions would have momentum on the order of a GV. If you're charitable, the lambda scale is about a GV. That means your derivative expansion is completely broken down.
Like Weinberg's ratio of the quark masses in terms of baryons.
Say it again.
In terms of baryons, the quark mass ratio, can it be write down?
There are two independent operators you can write down. Is that what you're asking?
And the quark mass ratio, like the Weinberg did for the meson.
No, so for most of the baryon mass comes from doesn't involve the quark masses. So taking ratios of baryon masses will never give you quark mass ratios. It will give you some horrible stuff. Given everything we know, can we get quark mass ratios from the baryons? I've never heard of that. Sorry. Yeah.
Take the ratio away.
It's a good question. I've never seen it done. Do you know whether anyone's ever tried calculating the quark mass ratios from the baryon masses? The electromagnetic corrections are nasty. There are several operators, and so you might have too many unknowns. I think you probably have too many unknowns to isolate the quark mass ratios the way Weinberg was able to do with the mesons. You have two electromagnetic mass corrections, I
Yeah.
believe. Two quark mass, independent quark mass operators. You've got the Carly invariant mass term. So right there, I count 6 independent parameters in the isospin limit. So I doubt you can get the quark mass ratio.
Can I ask a question?
What?
Can I ask a question?
Yeah.
So this redundancy in the description of baryon,
Yes.
the fact that you can add the U field, does it have any more significance, like some, I mean, the redundancy in the same of close to a gauge transformation or anything like that?
Not that I know of. I mean, we don't talk about it, but there's redundancy in how we define our electron field. We can, add some combination of photons to it, and that still will create an electron, and it would change your Lagrange and make it ugly, but probably do it. I don't know of any particular significance about this spaces.
Some effort was there in getting the rho as a hidden local.
Yeah, so there is some literature about treating the rho as a gauge boson. It's got some nice features, and I know that Georgi tried to make sense out of it by going to a large N limit of QCD, and he claimed that there was something called the vector limit, a non-conventional large N limit, which gave that result. This theory doesn't tell you anything about the rho, though. Yeah.
I've seen that in terms of the quark mass, to vary the quark masses from the lattice data, it goes quite far.
What?
The GMO relation, Gelman-Okobo mass relation.
Yeah.
Plot in terms of the quark masses. So that actually goes quite far, like still almost like the SU3.
You're talking about the meson mass relation. Yeah.
Not just.
Yeah. Okay. So
that's interesting.
Namani's mentioning that on the lattice, if you look at the quark mass, so one of the immediate predictions from Carl Lagrange, but it also, I think, probably goes back to Dashin's theorem, is that the meson mass squared is proportional to the quark mass. So that means that there's a linear relation between the mass squared of the meson versus the quark mass, and you check it on the lattice, and you ask, well, how large a quark mass does this hold? Because obviously, as you take the quark mass larger and larger, the pion looks less and less like a Goldstone boson. So you might expect this linear relation to break down as you start seeing the higher order terms in the Lagrangian. And it works astonishingly well to extremely high quark mass, what, 700 MeV or something? No, it's one of the mysteries of QCD why that's true. So that tells you that the higher order terms in the quark mass are actually unusually small, surprisingly small.